Hello, trying to be extra quick today with the last two dot points of section 2 of module 5. These two parts are still about uniform circular motion. So the first one, the relationship between the total energy, and the work done on object going in uniform circular motion. So intuitively, you'd say there probably shouldn't be any there shouldn't be any energy or work done on an object moving uniform circular motion because circular motion happens forever. There's no such thing as free energy. There's no way to just get energy constantly, more and more and more forever. Um, that's like some kind of perpetual motion machine, or it's well, this is a sort of a perpetual motion machine, but it'd be more than that. It'd be getting energy on top of the perpetual motion. And in nature, thermodynamics does not let us do that. So, um, mathematically, can we prove this to be the case? So, work, just so you know, work is a change in energy. So, if you add energy to something or you take energy away from something, you are doing work. So, these two things are asking sort of the same thing. So, if we have an object moving in circular motion, let's just say it's the moon moving around the Earth. We have the Earth down here, there's a little Australia, and this up here is the moon. I can give it some craters or something, right? The moon's going in this direction around the Earth. So you might say, okay, so a few different ways to look at it. We've got its gravitational potential energy, it's EG, and the moon stays sort of at the same height above the Earth at all times. Um, Therefore, especially if it's in uniform circular motion. Now, the motion of the moon is not uniform circular motion. It's a bit of an ellipse, but let's just pretend. Its gravitational potential energy is going to be constant. It's the same height above the Earth here, as it is here, as it is here, as it is here, although I haven't drawn it very well. And so, because it's the same height away at all times, the gravitational potential energy does not change. But what about its kinetic energy? You might say, well, its kinetic energy, it's got a velocity in this direction when it's up here, and it's got the exact opposite velocity down here. There is a force on the moon, and that force surely will do work. We have work equals force times displacement. Didn't draw that very well. Work equals force times displacement, and we have the kinetic energy equation, which cares about the velocity of the object. Energy kinetic is equal to half mv squared. So surely if the velocity is changing direction and if there's a force on the object, then there will be work done. But you'll see that this squared in this equation here, E kinetic energy equals half mv squared. If we take this value here as velocity and we square it, and we take this value here, which should be the same value, just in the opposite direction, so it might be negative, but when we square it, they actually both come out as the same value. So if velocity was, say, I don't know how fast the moon goes. Let's just say 10,000 meters per second. It's probably too far. Should be going pretty fast. Let's say it's 1,000 meters per second. Then this one will be 1,000 meters per second. The one down here will be negative 1,000 meters per second. So 1,000 squared, you get 100,000. 1,000 squared, you get 1,000,000 meters per second, and negative 1,000 squared, you get 1,000,000 meters per second. So the kinetic energy is going to come out as the same value, um, no matter what. No matter what position it's in, no matter what direction the velocity is going, it's going to come out the same. For this one, if you look at, say, the total displacement, the moon starts here, it eventually gets the same spot. Displacement is 0, work is 0. Even in an ellipse, we don't need to go into this, and I knew I wanted to make this quick, but whatever. So say if the moon was moving in an ellipse, it actually trades off between the kinetic and the gravitational. So when it's closer, it's got less gravitational potential energy. So in this spot, it actually is moving faster. It shifts its gravitational potential energy into its kinetic. And when it's further away, it actually moves slower to account for the higher gravitational potential energy that it has there, always maintaining the same total amount of energy. Okay, what about this one? And this is a related dot point as well. The relationship between rotation and torque. So really, I just want to go through what these equations are saying. So we've got this funny symbol here, um, which is really just taking the place of sine theta. So this symbol here means perpendicular to. It's more like that. Okay, it means that torque is equal to the radius times force, the force that's perpendicular to that radius. So let's try to draw a wrench. Torque is a turning force. Oh, look at this wrench. I'm going to screw it up. No, I'm okay. We've got a wrench and it's got a pivot point, which is the center here of the nut bolt thing that it's trying to turn. And you're going to put a force on this wrench. You're going to put a force right here going down there. So the radius of this is between the center of the pivot and the spot where you're applying the force. That is the radius, and the amount of force obviously is the amount of force, the size of this force vector here. So you grab the wrench, you pull it down, that turns the system. How much torque is applied? Well, the torque is equal to the radius times the force. So if the radius is 2 meters and the force is 2 newtons, you're doing 4 units of torque. What happens if your force is at an angle? So if you're not very good at using a wrench and you're applying a force, let's say you want to go in the opposite direction, but you're applying a force this way for some reason. I'm telling you one thing, you're wasting a lot of energy. You're probably going to pull your wrench away from the thing. But anyway, um, it's only going to count the um, amount of that vector which is perpendicular to this radius. So it's only going to count this much, this component of the vector, the perpendicular component. This component here is not going to be counted at all. This, I guess, parallel component. Okay, and how would you find this component? You do a bit of trigonometry. So if you know the force, you know the angle at which that force is being applied, you would use trig to find force at the angle. So the force that you want is going to be equal to, let's see, it's going to be sine theta equals opposite. Oh wait, that's not opposite. I've drawn the wrong angle. Okay, it's going to be, oh, this is going to get messy. Let me erase some stuff. Okay, not too bad. So the angle is going to be defined as the angle like thus. There we go. There we go. The angle between the line of the radius and the force you're applying. And so there's that component of the vector there. And we're going to have the blue component, which is coming up here. Boom. It's the blue component that's perpendicular to the radius. That's the one we care about. So sine theta is going to equal opposite. That's the force we want over hypotenuse. So if we rearrange that, it's going to be sine theta times the applied force. That is the force in black times force is going to equal the perpendicular force. We can even draw one of these. It's going to equal perpendicular force. Like so. Sine theta times force is going to equal to perpendicular force. Sine theta times force times radius is going to give you the amount of torque. And that's it. This is actually an important equation to learn because torque is going to come up in later topics. You need torque to learn about motors that spin. You need torque to potentially learn about how particles will move around in magnetic fields, like charged particles moving in magnetic fields. So this is not one to forget.